Welcome, everyone. This is part 2 in our series on analysis methods in NLP. We're going to be talking about adversarial testing. This is an exciting mode because, as you'll see, with a few dozen carefully created examples, you could learn something really interesting about the systems that you're developing. To start, let's remind ourselves of how evaluations standardly work in our field. At step 1, you create a data set from some single homogeneous process. It could be that you scrape data from the web or crowdsource a data set or label examples yourself. But the important thing is that we typically do this as one single process. And then in step 2, we divide that data set into disjoint train and test sets, and we set the test set aside. And you do all your development on the train set, and only after all development is complete, you do an evaluation of your system, usually based on accuracy or some similar metric, on that held out test set. And then finally, and this is the important part, you report the results of that test set evaluation as providing an estimate of the system's capacity to generalize to new experiences. I hope you can hear in that we're being awfully generous to our systems. At step 1, we create a single data set from a single process. We hold out the test set, and we use that test set as our device for measuring how well the system is going to do if deployed out in the real world. But of course, we know that the real world is not created from some single homogeneous process. We know in our heart of hearts that if we deploy the system, it will encounter examples that are entirely unlike those that it saw in training and assessment in this standard mode. And that might worry us that we're overstating the capacity of our systems to actually deal with the complexity of the world. And adversarial evaluations are one way that we can begin to close this gap here. So in adversarial evaluations, we create a data set by whatever means you like at step 1. And you develop and assess the system using that data set according to whatever protocols you choose. It could be the standard evaluation mode if you like. Here's the new part. At step 3, you develop a new test set of examples that you suspect or know will be challenging given your system and the original data set that it was trained on. And then, as usual, after all your system development is complete, you evaluate the system, usually based on accuracy again, on that new test data set. And that's the result that you report as your system's capacity to generalize to new experiences, at least of the sort that you carved out in your adversarial test set. And the idea here is that in having a distinction between the data that we develop our system on and the challenge problems that we pose, we'll get a better estimate of how our systems perform on examples that are presumably important examples that it's likely to encounter if deployed in the real world. A brief historical note, I think it's fair to say that the idea of adversarial testing traces all the way back to the Turing test, which is introduced by Turing in this classic paper, Computing Machinery and Intelligence. The Turing test has an inherently adversarial flavor to it because, of course, a computer is trying to trick a human into thinking that the computer is human. We also hear echoes of adversarial testing in this classic article/book from Terry Winograd called Understanding Natural Language. There are discussions in that book of the idea of constructing examples that we know will stress test our systems by probing to see whether they have knowledge of what the world is like and the true complexity of language. And then I think Hector Levesque really elevated those Winograd ideas into a full-fledged testing mode in his paper on our best behavior. Let's look briefly at those Winograd sentences or Winograd schema because they're kind of interesting. The idea is that they will key into whether a system has deep knowledge of the world and of language. So we start with an example like, the trophy doesn't fit into the brown suitcase because it's too small. What's too small? And the human answer is the suitcase. There's a minimally contrasting example. The trophy doesn't fit into the brown suitcase because it's too large. What's too large? Here we answer the trophy. And presumably we do this because we can do a kind of mental simulation involving suitcases and trophies and figure out how to answer these questions on that basis. This next pair of examples is similar, but it keys more into kind of normative social roles. The council refused the demonstrators a permit because they feared violence. Who feared violence? And our standard answer, drawing on standard social roles, is the council. Again, we have a minimally contrasting example. The council refused the demonstrators a permit because they advocated violence. Who advocated violence? And here, again, drawing on default social roles, we're inclined to answer the demonstrators. The intuition, as I said, is that to resolve these questions, given how minimally different these examples are, you need to have a deep understanding of the questions and the context, and also a deep understanding of what our world is like. And then, as I said, Levesque kind of continues this and begins to systematize it. So he says, we should pose questions to our systems like, could a crocodile run a steeplechase? And the intuition is clear. The question can be answered by thinking it through. A crocodile has short legs. The hedges in a steeplechase would be too tall for the crocodile to jump over. So no, a crocodile cannot run a steeplechase. Again, a kind of mental simulation that leads us to an answer to this surprising question. And the idea is that questions like this will not be susceptible to cheap tricks. As Levesque says, can we find questions where cheap tricks like this will not be sufficient to produce the desired behavior? This unfortunately has no easy answer. The best we can do, perhaps, is to come up with a suite of multiple choice questions carefully, and then study the sorts of computer programs that might be able to answer them. I think you can hear in that what we now call the adversarial testing mode. Now, I'm encouraging you to pose adversarial tests to your systems. And as I said, you can do that by constructing just a few novel examples. But we should be aware of what we're doing. Primary question, what can adversarial testing tell us, and what can it tell us about the systems that we're developing? So here are just a few considerations that should guide your work in this area. First, you don't need to be too adversarial. It could just be that you're posing a challenge problem to assess whether your system has an understanding of a particular set of phenomena. Has my system learned anything about numerical terms? Does my system understand how negation works? Does my system work with a new style or genre? These are challenge problems that you could pose open-mindedly, and you might find that your system is surprisingly good at them. Second consideration, we should be thoughtful about the metrics we use. As I signaled to you before, the limitations of accuracy-based metrics like F1 and so forth are generally left unaddressed by the adversarial paradigm. And that's because we want a minimal contrast with our standard evaluation modes. But I think you can hear in the mission statements, especially from Levesque, that we might at some point want to break free of that very restrictive mode and pose more open-ended, complex evaluations for our systems that would involve requiring them to offer their evidence and interact with us to resolve uncertainty about what they're supposed to be due. All of that is kind of left aside in the standard adversarial mode, and we should be aware that it's a limitation. This next question is really fundamentally important. In adversarial testing, if you see a model failure, is it actually a failure of the model or of the data set that the model was trained on? Leo et al. Posed this nicely. What should we conclude when a system fails on a challenge data set? In some cases, a challenge might exploit blind spots in the design of the original data set. That would be a data set weakness. In others, the challenge might expose an inherent inability of a particular model family to handle certain natural language phenomena. That would be a model weakness. Now, these are interestingly different from the point of view of development in our field. We're apt to hope, I think, that we find model weaknesses because those are really fundamental discoveries. But we should be aware that it might be that the system could have done well on our adversarial test if it had just been trained on the right kind of examples, and that would be a data set weakness. Data set weaknesses are presumably relatively easy for us to address. We can just supplement the training data with examples of the relevant kind, whereas model weaknesses are forcing us to confront something that might be an inherent limitation of the set of approaches that we're taking, a much more fundamental insight. Atticus Geiger et al. In this paper offer a similar insight in the context of being fair to our models. For any evaluation method, we should ask whether it's fair. Has the model been shown data sufficient to support the kind of generalization we're asking of it? Unless we can say yes with complete certainty, we can't be sure whether a failed evaluation traces to a model limitation or a data limitation that no model could overcome. And I'm emphasizing this because it's surprisingly easy to fall into the trap of thinking you have imposed an unambiguous learning target when in fact you have not. Just think about this simple example here, human to human. Suppose I begin the sequence 3354 and I say to you, what comes next in the sequence? Now, I might have in mind the number 7, but the evidence that I have offered you wildly underdetermines how to continue the sequence. And so I think it's fair to say that no learning agent without a lot of ambiguity could figure out what my intended continuation is. And sometimes our adversarial tests have this quality that the available data and experiences of these systems just don't fully disambiguate what our intended learning targets are. So we should be aware of that. Those are data set failings rather than model failings. Now, I can offer you a constructive set of techniques to figure out whether you're dealing with a data set weakness or a model weakness, and that falls under the heading of inoculation by fine-tuning from this wonderful paper, Liu et al., that I quoted from before. So Liu et al. Just to remind us that in this standard challenge evaluation mode, we train our system on some original data set, and then we test it on both the original test set and our challenge test set. And our expectation is that we'll see outcomes like this, where the system does really well on the original data, the original test set, and really poorly on the challenge test set. But when we see this outcome, we should ask why this is happening. In particular, is it a model weakness or a data set weakness? And their proposed method, this inoculation method, works as follows. We're going to fine-tune our system on a few of our challenge examples, and then retest on both the original test set and the held out parts of the challenge test set. When we do this, there are kind of three classes of outcome that you might see. The first would point to a data set weakness. If via this little bit of fine-tuning on the challenge data set, we can get good performance on the original and the challenge data set, that shows us that in this original evaluation mode, the system just didn't see enough of the relevant kinds of examples from your adversarial test to have any hope of succeeding. But a modest amount of training on those examples leads it to do fine. That's a data set weakness. A model weakness is what we might have in the back of our minds for our adversarial testing. And this would be the case where even though we have fine-tuned our system on some of these challenge examples, its performance remains really low, even though the system can maintain good performance on the original data set. And this is just like there is something special about these new examples, and the model simply cannot get traction. And there's a third outcome that might be really worrisome, and they would trace this to kind of like annotation artifacts or label shift or something like that. And that's where in doing this fine tuning on some challenge examples, we see degraded performance on both the original data set and the challenge data set. And that would show that there is something fundamentally confusing about these adversarial testing examples that are causing a lot of problems for the system that we've developed, because even a modest amount of fine tuning causes kind of consequences to ripple through the system that are impacting even performance on the original data set. All right, to close out the screencast, let me offer you two examples of interesting adversarial tests in our field, beginning with the SQUAD question answering data set. I showed you this leaderboard from SQUAD 2.0 at the start of the quarter. And the funny thing, of course, is that you have to go all the way to place 13 on the leaderboard to find a system that is worse than our estimate of human performance. So we have superhuman performance on SQUAD, but what does that really mean? SQUAD was also the site of one of the first really systematic adversarial testing efforts in our field. This is from Jia and Liang 2017. And what they did is quite simple. We begin with SQUAD examples where we have passages and questions as inputs, and the system task is to answer the question, and we can count on the answer being a literal substring in the passage that the system was given. The adversarial thing that Jia and Liang did was simply to append misleading sentences to the ends of those passages. And what they found is that systems were systematically misled by those final sentences. Whereas humans could easily ignore them, systems were now inclined to answer drawing on information from those misleading new sentences. And this is kind of an interesting dynamic because you might think, well, we'll just train our system now on passages that have these augmented misleading sentences, and then surely our systems will be more robust. That might be true in some sense, but of course we could then just append sentences to the start of the passages. And Jia and Liang found that systems were now confused by the appended initial sentences, and they started to give wrong answers in that mode as well. And you could kind of go back and forth in this adversarial mode, showing that systems were worrisomely easy to trick based on these simple appending of misleading sentences. Now, that's a very interesting about adversarial evaluation mode. What I think is more interesting about the outcomes is that they begin to show us just how different adversarial testing can be. So here's the SQUAD leaderboard, the original at the time of the paper, as well as the results of this adversarial test. And you can see, first of all, that system performance has really plummeted. So this turns out to be highly adversarial to these systems for whatever reason. I think it's more interesting to note that the system ranking has really been mixed up. So it's not like the systems uniformly dropped in performance. Now, as we move from the original rank to the adversarial rank, we have like the first place system is now in place 5. The second has dropped all the way to place 10. But the seventh place system is now in first place. It looks kind of chaotic. Here's a scatter plot where we have the original system performance along the x-axis and the adversarial system performance along the y-axis. And you can see that it's kind of chaotic. There's no way that one predicts the other. So something very interesting has happened. And that's noteworthy because it looks like that's meaningfully different from what we do when we do standard evaluations. I don't have direct evidence of this from Squad, but here's a case where people took two classic image data sets and simply created new test sets according to the same protocols that were used for the original dataset test sets. And what you find is a very strong correlation. Even though the examples are new, because it's the same protocol, system performance is highly predictive in the sense that the original test accuracy is perfectly correlated with accuracy on these new test sets. Very different from this adversarial mode where something much more chaotic happened. So adversarial testing is meaningfully different, it seems, from standard evaluations. Let's move to NLI now. This will tell us two different lessons about how adversarial testing can be informative. So we saw at the start of the course that we now have superhuman performance on the SNLI dataset. That's certainly noteworthy. And we're reaching superhuman performance on the MultiNLI test set. We're sure to be there if we're not already at the time of this screencast. But we've also seen that systems that perform really well on these data sets are often susceptible to adversaries. In the first screencast, I showed you these examples from Glockner et al.'s Breaking NLI paper, where they make simple modifications to these hypotheses and find that systems do not behave systematically with respect to human intuitions about the modified examples. And that's the worrisome part. And they quantify that, of course, and that you can see that the best systems at the time up here were doing pretty well on SNLI, and their performance plummeted on these new test sets, showing that this was, for whatever reason, truly adversarial when it comes to those systems. But I also presented this as a story of progress, right? Because I showed you that in simply downloading Roberta MultiNLI, that is Roberta fine-tuned on the MultiNLI dataset, you now have a device where with no work, you can essentially solve this adversarial test. I think that's really striking, and it points to the fact that Roberta, unlike those earlier models, might truly have systematic understanding of the relevant kinds of lexical relationships that you need to solve this adversarial test set. So that's an exciting outcome. Here's a second outcome that you might see, and this is from the Naik et al. Paper that does a wide battery of different adversarial tests on MultiNLI data. They did a bunch of things like antonyms, I love the Cinderella story, contradicts, I hate the Cinderella story, just drawing on lexical knowledge. They asked about numerical reasoning across these two premises, word overlap, and this is a little bit different in that you're doing something like just inserting material that you might think is going to be distracting in the mode of the Squad adversary and seeing what effects that has. And the same thing for negation, adding on to the end information that's going to be misleading for a system and also includes a lot of negation elements. And there are a few other modes that I didn't have space for. It's a very rich paper with a very fine-grained breakdown of how systems do on these different adversarial problems. Here's a picture of the data set, and here's a breakdown. And I think the overall takeaway is that the numbers across the board are very low on these adversaries. And so that's interesting. And it looks like even top performing systems for MultiNLI are stumbling with these problems that we surely want our systems to be able to solve if we're going to call them true common sense reasoners. However, this was actually the basis for a number of the experiments in that inoculation by fine-tuning paper that I quoted from before. Here's a kind of rough picture of the performance results that they report on different subsets of that adversarial test on MultiNLI. And you can see that it shows all the different outcomes that we discussed under the heading of inoculation by fine-tuning. To simplify things, just focus in on the green lines. The ones with dots are the original system performance, and the ones with crosses are on the challenge data set. So this first column here is identifying data set weaknesses. What you're seeing is that as we fine-tune on more examples from the challenge data set, going along the x-axis here, we very quickly get a system that's actually good at this challenge problem, right? After just about 50 examples, the system is basically learning to solve the word overlap and negation problems, although negation takes a little bit longer at 400 examples. So that's a case where the original systems were failing, not because of any intrinsic property of the models being used, but rather because the data clearly just didn't have enough information to resolve these learning targets. We also see outcome 2, which is a model weakness. Again, follow the green lines, and you can see here that for spelling errors and length mismatch, no amount of fine-tuning on challenge examples helps these systems get traction on these problems. That's these flat lines here. And that's showing that there's something fundamentally wrong possibly with these models. They are just unable to solve these 2 challenge problems. And then we also see the third artifact for numerical reasoning. You'll notice that system performance is kind of really chaotic here. And that's suggesting that there is something importantly and problematically different about these challenge examples, because fine-tuning on them causes the system to become really chaotic in its predictions when we get degraded performance, not only on the challenge set, but also on the original data set, showing that we've done something quite disruptive. So this is really interesting that in this case, from this battery of adversarial tests, we see all these different outcomes pointing us to all sorts of different lessons about what action we should take to make these systems more robust.